Now that you've seen how we can customize the completable future framework to use virtual threads, let's go back and revisit some examples that we looked at with the PrimeCheck application case study. And in particular, we're going to see how we can have a couple of different implementations of completable futures, one of which will use the normal thread pool model, and the other of which will use the new version we saw that will use a virtual thread for each of the asynchronous requests. So that's basically the new example we're going to look at. And this example, as usual, can be found in the EX1 folder, the EX1 project, in my web MVC folder, in my live lessons GitHub repository. So here we are in the project, and what we're going to do here is take a look at a couple of different implementation strategies involving completable futures. So first, let's take a look at one that just uses completable futures the normal way you get out of the box with Java 8 and beyond. This is the PC completable future strategy, which implements the PC abstract strategy. And you can see here that it's got an overridden method called checkIfPrimeList, which takes a list of integers and a Boolean parameter. And the Boolean parameter indicates whether we want to run things in parallel or not. And so what we're going to do is, if the flag parallel is set, we're going to make the thread pool be the Java common fork join pool. Otherwise, we're going to make a thread pool that has a single thread. So it's a thread pool of one. So it's single threaded. And then what we're going to do is we're going to go and take the list of prime candidates, turn it into a stream of prime candidates, and then we're going to asynchronously check each prime candidate for primality. So for each of these prime candidates, we're going to go ahead and submit it to the completable futures framework using the supply async factory method. And what supply async is going to do is it's going to arrange to call the isPrime supplier in a background thread in either the common fork join pool if we're running in parallel, or in a single thread if we're not running in parallel. And it's going to pass in the executor, which is the variable that we defined up here in the try with resources block. It's going to go ahead and pass that in to supply sync so that it can go ahead and execute it in the right executor. So what's going to happen then is all those calls, let's say there's 1,000 of them, there's going to be 1,000 suppliers that are going to be given to the completable futures framework. And assuming we're running in parallel, it'll then go ahead and run all those things in the background. And then we're going to collect the results using this futures collector. And the futures collector is something that we've looked at before. Basically, what it's going to do is it's going to implement the collector interface, and it's going to take a stream of completable futures to type T, which in our case, of course, are going to be these integers. And it's going to store them in a list of completable futures of type T. And then when it's done, it's going to return a completable future to a list of objects of type T. And most of this stuff is pretty boilerplate. We have a supplier that makes an array list, an accumulator that goes ahead and adds the next item to the array list. We have this combiner that we're not using because we're not using parallel streams. And then we have this finisher, and the finisher is where all the exciting stuff happens. So the finisher method here, which is a little bit hard to read because it has a long return value type, it's going to take the list of completable futures, the objects of type T, and it's going to use the all_of method. This is one of those invoke all methods that are available in completable futures. And it's going to essentially wait for all the completable futures in that list to finish. So it's going to return a completable future that, when notified or when triggered, indicates that all the asynchronous computations have finished running in the background. And in that case, we're going to have a completion stage method that will take the list of completable futures we had to begin with, join all of them because they've all finished. We wouldn't have gotten to this point unless everything was done. And then we're going to create a list that will be a list of the results of the asynchronous computations, and then apply returns a completable future to this said list of results. And so that'll get called back when everything else is finished. And then so this will get back a single completable future that will trigger only when all the other ones are done running. And then we call the join method, which will block until all the asynchronous processing in this whole stream completes. And then when we're done there, we print out a diagnostic and return the results. So that's how we're going to do this with the standard out-of-the-box implementation of completable futures. And we can switch back and forth between using the common fork join pool or just a single threaded executor. Now let's turn our attention to another way to do this, and this approach is going to use the completable futures EX customization of the completable futures framework. So here is the check if prime list method using this approach, and you can see this looks very similar. The difference being that we're going to make a new virtual thread per task executor if this is parallel, if parallel is true. Otherwise, we'll do a single-threaded one again, so we can swap back and forth between concurrent and single-threaded. And then down here, everything looks absolutely identical, except rather than using completable future, which is what we had in this strategy here, where you can see we said completable future, instead, we're going to have completable future EX. Everything else is the same. We're going to create a different completable future subclass, and this is going to be the one that will use the new virtual thread per task executor if that's what was designated by the client. So let's go take a quick look at that. We've seen this before, but this is a bit more thorough walkthrough of it. So completable future EX extends completable future, and it defines this private static field, which will, by default, allocate a new virtual thread per task. We have a helper method called setExecutor, which will take the current value and then update it and return the old value. So we can change this if we want. Here's the default executor hook method, which is overriding the subclass, or the base class, superclass version that returns sexec. New incomplete future just makes a new incomplete future EX that doesn't have anything associated with it yet. And then we've got two methods here, one called supply async that takes just a supplier, and it assumes that whatever the default implementation of, or whatever the current implementation of sexec is will be used here. And so that goes ahead and creates a new empty completable future and then completes it with the supplier. And then we have a second implementation, which is what we're actually using in the code in our PC completable future EX strategy implementation. We have another one that takes an executor as the second parameter. And you can see what it does is it checks to see whether the executor matches the current executor. If it does, we've already got this set up. Otherwise, we set the executor to be this one. And then we call new completable future EX complete async with a supplier. So what this does is this will allow us to systematically override the hooks in the completable future framework to ensure that a new virtual thread is created for every asynchronous operation. Now, that, of course, raises the question, how does this perform relative to the other approach? So to find the answer to that question, let's go ahead and run the test. And this particular test will go ahead and just run all the different variants of the normal completable future strategy, namely the ones that use parallel individual calls, sequential individual calls, parallel list calls, and sequential list calls. And so all those things will go ahead and run with the normal version of the completable future framework. And then we're going to go see what happens when we run it with the version of the framework that uses the custom completable futures that allocates a new virtual thread for every one of the requests that are running in parallel. So you can see we've given it a count of 500 random integers to check the primality of, and it's just going through all the permutations, list call, sequential, completable future, individual call, and so on. And then when we're finally done with this thing, you can see the results. And what's interesting here, I think it's really quite interesting, the version that used the completable future EX with the virtual threads for this particular run actually performed better than the one that used the default completable future implementation that uses a pool of platform threads, showing that at least for this type of computation, which is admittedly heavily CPU bound, because we're just checking to see whether or not the numbers are prime, so there's no blocking going on, that virtual threads are indeed very, very, very efficient. Now, if we ran this a couple times, we might get slightly different results, but there's not an appreciable difference between the results. And of course, what you also see here is that the list calls are the fastest, which we saw before. We would expect that. The individual calls that run in parallel are also faster than the sequential versions. And then the ones that run lists with sequential versions are faster than the ones that run individual. And again, this is all fairly intuitive because of the fact that the individual calls have to do this round trip from the client to the server process for every integer we're checking the primality of, whereas the list call ones passes them over in one fell swoop and does all the processing en masse. So that's the end of the discussion of this particular implementation.